let's start by looking at Newton's laws. His first law says that an object at rest remains at rest, and an object in motion remains in motion, unless it's acted on by an unbalanced external force. The second law, which is the law we're going to be using primarily in this class, says that when an object is exposed to an unbalanced force, it will accelerate in the direction of the resultant force, or the sum of the forces. Mathematically, this says F is equal to ma. This is the equation that in statics we had A equal to 0, so this was the equation that gave us sum of forces in the x is equal to 0, sum of forces in the y is equal to 0. Newton's third law says that mutual forces of action and reaction between particles are equal, opposite, and collinear. This means that if I push on the wall is pushing back at me. We used this in statics when we separated free body diagrams, and the forces between the two bodies that we separated were equal and opposite. Newton also came up with the law of gravitational attraction, which mathematically says that the force between two particles, or two objects, is equal to g, which is a constant, times the product of the two masses divided by the distance between them squared. We'll take a little bit of a closer look at that on the next slide. One thing to note is that Newton's laws come from classical physics. Classical physics does not apply when things start moving at very high speed, so approaching the speed of light, for example, or when particles are very, very small, so when you're dealing with electrons and atoms. These laws will not be useful. However, in general, most engineering happens on the macro scale, in the real world type interactions, where Newton's laws do apply. So let's take a look at mass and weight. Weight is the force of gravity on an object. Okay? It's measured in newtons or in pounds, and it's given by Newton's law. If we take a closer look here, g is a constant, given as 66.7 times 10 to the negative third. The masses are of the two objects, so let's take some object, m2, and the Earth being the other object. So the mass of the Earth is 5.9742 times 10 to the 24th kilograms. And we'll look at the surface of the Earth. So we're going to look at the radius of the Earth. If we plug that in, we get 9.79982 times m2, whatever our object is. This should look familiar. This, right, is g, the acceleration of gravity. 9.81 meters per second squared if you're using SI, or 32.2 feet squared if you're using US customary. So g is just an acceleration, so really this force equals g m1 m2 over r squared is rewriting of F equal to ma. Units, newtons if you're in SI, pound force if you're in US customary. Mass, on the other hand, is the measure of the resistance of a body to a change in velocity. A change in velocity being acceleration, so basically we're defining mass through this equation. It's also the amount of matter in an object. It's an absolute property, which means the mass of something doesn't depend on where it's at, whereas the weight of something does. So my water bottle on Earth weighs something different than it would on the moon, but its mass is the same. The units for mass are kilograms in SI or slugs in US customary. Make sure you don't use pound masses. Sometimes textbooks or engineers will use pound masses. Convert it to slug before you use F equals ma, or it will not work. And one slug is equal to 32.2 pound mass. So this gives us a sense for mass and weight. We did this in statics, but it can't hurt to review. Alright, so with that in the background, we now can look at this F equal to ma that we're going to use over and over and over again in this class. In statics, ma was 0. So we had some of the forces in x equal to 0, some of the forces in y equal to 0, some of the forces in z equal to 0. Now we could have accelerations in each of those directions. So we have some of the forces in x equal to mass times the acceleration in x, and so forth. The way we go about solving these problems is first to identify an inertial reference frame. That means that our reference frame can't be accelerating. Alright? We assume in general in engineering that the Earth is an inertial reference frame. Technically that's not right, because the Earth is moving in an ellipse around the Sun, so it's got an acceleration because it's on a curve. But in general we assume that the Earth is not accelerating. We ignore that acceleration for the purpose of solving these problems. But for example, you couldn't pick a reference frame that was on an accelerating train, for example. That would not work. Then we place our x, y, z axes, and there's nothing special about horizontal and vertical. So long as those axes are perpendicular to each other, we can place them at any angle. And we draw a free body diagram. Remember, when we draw a free body diagram, we take all the other objects away. We're only looking at the body we're interested in. And any object we remove is replaced by a force. And since we remove the Earth, we always replace the Earth by the weight of the object. Then we identify the expected direction of our acceleration. We're going to define this as positive. This doesn't really matter if we don't know. We can just guess a direction. But just make sure you indicate your positive direction somewhere on your piece of paper, so if you get a negative answer, you know what that means in terms of direction. Then we're going to apply our second law in each coordinate direction. And if we need to, we can always go back to the kinematic equations to find more information. So they might give us information about velocity. We don't need information about velocity for our problem. We need acceleration information. So we may have to use our kinematics in order to find those accelerations. So let's take a look at an example. It's a pulley example, so it'll be a good review of our pulleys from the last lesson. So let's see. We're told that we're trying to figure out what is the mass of block A. We're told that the mass of block B is 5 kilograms. And we're told that it's going to move up the slope. Right, so block A is going to move down, and it's going to move 0.75 meters up the slope. It's smooth, so no friction, and it's going to move that distance in 2 seconds. And it starts from rest. So what it's giving us is information about the kinematics. Alright, so we're told that the initial velocity is 0. The distance is 0.75, which is s minus s naught, and the time is 2 seconds. And we can neglect the mass of the various pulleys and ropes, so we're only interested in the masses of A and B. Alright, so in order to find the mass of A, let's talk about how this is working. The mass of A is going to create a tension in these ropes, right? Because it's going to be pulling down. It's going to create tension in those ropes. The tension in a rope is the same everywhere. So the tension in the rope then is going to be pulling on B and causing it to move up the slope. Okay, so that's the forces involved. So then, if B is accelerating, A is also going to be accelerating. And they're going to be related through those tensions. So let's start by figuring out what is the acceleration of B. Well, we're given an initial velocity, a distance, and a time. So we can look at our kinematic equations, and we have the one where s minus s naught, which we're calling D, is equal to v naught times t plus 1/2 at squared. Alright, so if we solve that, this is 0. We know D, we know T, so we can find A. A is equal to 0.375. So that's A of block B. How is A of block B related to A of block A? Since ultimately we're trying to find mass of block A. Well, that's a pulley system, right? So let's look at our pulley system. If this is our datum, we've got this distance, which is SB. We've got this distance, which is SA. And technically that's all we've got, but it looks like we have another distance, right? We have a distance that's from here to C. Let's look at SC. And we'll see in a minute why that's a constant, right? Because this is on a rigid bar. So SC is a constant, which means it's going to disappear from our equations. But let's write the length of the rope. That's how we deal with pulley systems. So the length of the rope is SB, it's this section, plus all the way down to SA, or SD, I guess, but plus S, let's call it SD, and let's change this. You should all be able to see how SD and SA are the same thing, since this is a rigid link. The length of that doesn't change. So plus SD, that's this line, and then we have two of these. So plus 2, and the length of this is SD minus SC. Alright, so if we take the derivatives, the length of the rope doesn't change, so that's 0. The change in distance with respect to time is the velocity B plus velocity D plus 2 velocity D, and SC is a constant, so it's the derivative of it is 0 as well. So we get that VB is equal to 3VD, and VD, let's see, VD is equal to VA. I like A better because we're talking about A, the block A. So this is 3VA. So accelerations are another derivative. So the acceleration of B is equal to 3 times the acceleration of A. If we know the acceleration of B is 0.375, then the acceleration of A is 0.125. Alright, so now we know information about the accelerations. That should mean that we can find information about the forces. So to do that, we're going to need information, free body diagrams. So we've got two bodies that we're interested in. We've got body B, which is on a slope, and we've got body A that is straight up and down. So if we draw the free body diagram of body A, we've got its weight pulling down, which is mass A times the acceleration of gravity. We don't know mass A, but that's what we're trying to find. And then we've got some tensions pulling up, right? So if we look, let's make body A this entire piece, okay? Then we look here, how many times do we go through that rope? 3 different times. So in each of those times we cut the rope, we have to replace the rope by its tension. So we've got 3 tensions pulling up. T, T, and T. So if we write our F equals ma, so it's, what way is this going to accelerate? Well, it's going to accelerate down. So we're going to write our force equation downwards. And this is for our body A. So we get the sum of the forces on this is 3t going up, which is negative because we define down as positive, plus ma times g going down, those are the forces, is equal to the mass times the acceleration a, which is 0.125. Alright, we don't know ma and we don't know t. So we're stuck at the moment on that one. Now let's look at the other body. So the other body is at a slant. So there's our box. We've got the normal force. There is no friction force. We've got one tension, right? Because if this is our body, we have to cut that rope, but there's only one rope. So tension always pulls in a rope. And we have the weight, which is coming straight down. So this is mBg. That's the normal force, and we've got the tension. It's going to accelerate upwards that way. That's our acceleration. So let's make our axis along the direction of the acceleration. We don't have to, but it's probably the easier way to do it. So we'll have one axis this way and one axis this way. If we look at that, then tension is all along one axis. Normal force is all along the other axis, and mBg, the weight, has a part on each one. Alright, so we're going to eventually write our equation going that way. Sum of forces is equal to mb ab. Alright, so we need to figure out what component of mBg is along this upward slope. So this angle here is 60 degrees. If we make this a triangle, if this is 60, then this bottom line makes 60 on the outside, which makes mean 30 is on the inside, or this angle up here is 60. Alright, so convince yourself of the geometry of that. Now we can write the sum of the forces along this upward slope. T is going up. mBg times, that would be the sine of 60, because it's opposite the angle we just drew, is going downwards. And that's equal to mb times ab. Well, we know AB, we know MB, we know MB, we know G, so we can find T. So T is equal to, mass B is 5. We are in SI units, so G is 9.81. Sine of 60 plus 5 times AB is 0.375. Allows us to find the tension of 44.35 newtons. So now, knowing tension, we can go back to the other block. If we know tension, we know G, we can find MA. So -3 times, we're going to bring this down here, right? -3 times 44.35 plus MA times 9.81 is equal to MA times 0.125. Solve for MA is equal to 13.7 kilograms. So that's our final answer. Alright, let's take another example. In this case, the acceleration is not going to be constant, which means instead of being able to use those nice simple kinematic equations where acceleration was constant, we're going to have to use our derivatives or our integrals. So, we've got a 2 megagram car. It's being towed by a winch. And that motor, this guy, is creating a tension in the rope of 100 times s plus 1. And so the car is being accelerated, because this isn't a constant, right? So that must mean that the car is being accelerated. And we want to know, what is its speed at s equal to 10? So we start with a free body diagram of the car. There's my car. It looks like a block. We've got a normal force. We've got a weight. So that's mg. We've got a normal force. We've got a tension. And it says we can neglect rolling resistance, so there's no friction. Okay. It's accelerating in this direction. So we write our Newton's second law for that direction is equal to ma. The sum of the forces, the only force acting in that direction is T, which is 100 times s plus 1 is equal to the mass, which is 2 megagrams. 2 megagrams is 2,000 kilograms, and we want our masses in kilograms. So that's 2,000 times A. So A is equal to 1 over 20 S plus 1. Alright, how do we find V from A? We could take a time derivative, but there's no time in this, right? We have an S, not a T in our equation. So if you think back to our kinematic equations, there was that combined equation, right? The one that said that A ds is equal to V dV. Well, now A is this expression. V is what we're looking for. So we're going to end up taking the integral of both sides to get V out, right? So we've got the integral from 0 to the S we're interested in, which is 10, of 1/20th S plus 1 ds is equal to integral from 0 to our final V, because it started from rest, so that's where the 0 is coming from, of V dV. Alright, if we take these integrals, the 1/20th comes out, we get 1/2 S squared plus S, evaluated from 0 to 10, is equal to 1/2 V squared, evaluated from 0 to V, so it's just V. Plug in 10 for S, and solve, we will get 450 is equal to 1/2 V squared, or V is equal to 30 meters per second. So, a couple of special situations. First of all, usually we have a whole bunch of particles, or a solid object that is made up of a whole bunch of particles, right? We don't have single particles, though sometimes we can assume we have things act like single particles. Alright, so if we can lump these particles together to create a solid body, we still have the same equation. Alright? Sum of forces equals mass times acceleration. But the acceleration of what? If you clump a whole bunch of particles together, it could be that some of those particles aren't accelerating at the same rate as other particles. So what we use is the acceleration of the center of gravity. Thinking back to statics, we found the center of gravity for various objects, right? There was a whole big process, and we'll revisit that when we get to the point where we're doing it here. M is just the sum of the masses of all the little particles, so it's the mass of the whole body together. Okay. Something else that we saw in statics that we'll have to factor into dynamics as well is friction. So if we remember friction always acts to oppose the motion, right? So if an object is moving to the right, friction is going to be to the left. There's two types of friction. There's kinetic friction, which is occurring when an object moves over a rough surface. So we've got a moving object, which is why it's called kinetic, and the surface is rough, so there's a friction. There's also static friction, which prevents an object from moving. So you've got static friction up until the point it moves, and then you've got kinetic friction after it starts moving. Static friction is, in the vast majority of cases, bigger than kinetic friction. Okay? So that's why you pull hard to get something to move, but once it's moving, it's easier to pull. That's the effect that you're feeling there. The equation for friction is the force of friction is equal to mu, where you've got a mu k or a mu s, depending on which friction you're looking at, times the normal force. So we'll be looking at an example using friction in a second. The other thing that can create forces often are springs. So we've got elastic springs. They create a force based on how much they're stretched or compressed. So S is the change in spring length. There's nothing special about S. You could call it X, you could call it delta L, whatever you want to call it, but that's the distance that the spring is stretched or compressed. K is the spring constant for that spring, which is usually given to you. Something to notice, because of the way this is written, if you stretch a spring only a little bit, you're going to have a smaller force than if you stretch the spring a lot. That means your force isn't constant. If your force isn't constant, your acceleration is not constant either, which means you can't use the constant acceleration kinematic equations. You're going to have to use integrals or derivatives. And we'll see that in an example as well.